Good morning, ladies and gentlemen. Today we're going to be starting section 4.6, related rates, which technically is an application of the derivative. Whoa. It's an application of the derivative, okay? And it's also going to be an application of implicit differentiation, as well as the chain rule, because implicit differentiation and the chain rule go hand in hand. And what we're going to be doing here on related rates is we are going to be differentiating with respect to time, and it's going to feel kind of awkward in the beginning because you're going to be like, whoa, I'm going to be taking the derivative of a variable that's not even present in my equation. But before we get into that, we're going to set a small little foundation here. Derivatives. Well, what are derivatives? They are a ratio of the change of two variables. Just like all the way back in Algebra 1, when you were working with derivatives in Algebra 1. Really? Yes. We took the change in y over the change in x, didn't we? And that's what we called it. It's y2 minus y1 over x2 minus x1. It got consolidated to change in y over change in x. But, you know, because now that we're in calculus, we like to impress other people with notation, namely differentials. So we don't call it delta y over delta x anymore. We pretty much, in calculus, we're going to call it dy dx, okay? And it's a little differential that's like a secret language that only calculus people understand, okay? And velocity. Well, what is velocity? Well, velocity in the beginning, well, that's change in distance divided by change in time. And of course, because we're in calculus, we want to know the change in distance, we can express that using differentials, calling it dd over dt, change in distance over change in time. Acceleration we also learned. Well, what is acceleration? Well, check out how that goes. Velocity, I'm not taking. A lot of people made that mistake on a test a while ago when you were finding average velocity. When you were finding the AROC of velocity, you actually find change in distance divided by time, because that's where you get your feet per second or inches per second. And acceleration, well, what is acceleration? Well, that's really change in velocity over change in time, right? And expressed as a differential, we would call it dv dt. And you're going to really have to pay attention to the types of problems we're looking at, because acceleration can be dv, as well as the change in volume can be dv as well, okay? So we're going to build on our little secret language of differentials here for a little bit. And notation, okay? Well, related rates are all about notation, notation, notation. We got to keep things straight. And if I'm thinking, okay, well, if y equals 3x squared minus 6x plus 2, well, I know that if I'm looking at that graphically, my independent variable is x, my dependent variable is y, and if I needed to find my slope of the curve or of this parabola, I know I'm looking for change in y over change in x, correct? And I can kind of see that. Well, how do I get that? Because in calculus, we think of dy dx. So what do? Well, basically, okay, typically when we take derivatives, we generally take derivatives with respect to the dependent variable. Generally, okay? Today we're going to start breaking that rule. But if I did, okay, and like I said, this is all about implicit differentiation and the chain rule, notation, 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 okay? What is the derivative of y with respect to x? Again, we don't want to call it y prime. We are going to think about that as the derivative of y with respect to x. Well, that's dy dx equals, and what's the derivative of 3x squared? Well, that would be 2 times 3 or 6x, drop my power 1. Don't forget your chain rule with implicit differentiation. That would be a dx over dx yet, or times dx dx. But we're not going to write that. Minus the derivative of 6x is going to be 6 dx dx And then if I say plus 2, the derivative of 2 is actually going to be 0 dx dx, and it's not there. Therefore, we leave it there. So if my function y equals 3x squared minus 6x plus 2, then its related equation would be dy dx equals 6x minus 6. Okay, well, what happens if it's not something like that? What happens if I change the variables in it? Well, that really, excuse me, isn't a big deal, because now that I'm looking at this one, a equals pi r squared, well, think about it. My radius is my independent variable. My area is my dependent variable. So I can think of my slope of this thing as change in area over change in radius. Okay? How would I find that slope equation? Well, again, we're going to take the derivative. Typically, we take the derivative with respect to radius. And if I took the derivative of a with respect to r, I'm pretty sure you know we get dA dr. We're not going to call it a prime. And that's going to equal, well, remember pi, don't wait out on pi. Pi is just a constant, pi r squared. So I got to take 2 times pi, so I get 2 pi r, drop my power 1, and then my chain rule, I'm going to have a dr there, which I'm not going to write because that's 1. Well, as I look at my very last one, p equals negative 4.9 t squared plus 10t minus 6. Well, that seems like it's a position function. Okay, well, it is a position function. Well, what that's doing, that's relating time with position, right? And if I needed to know the slope of that equation, I know it's going to be the change in p over the change in time is really what I'm looking at. So what do? If I'm looking for the slope of that equation, what I do is I take the derivative with respect to time. So if I take the derivative of p with respect to t, I get dp dt equals, well, negative 4.9 times 2, that's negative 9.8t, 0.8t, dt dt, which I don't write, plus derivative of 10t is going to be 10, derivative of that t is 1, so it's 10 dt dt, which I don't write, and bottom line, I get my velocity function out of that, okay? It's all about notation. It's all about impressing your friends, utilizing differential notation, okay? And when I'm talking about related rates, that's what I want. I want differential notation. And, well, what I want to do here is I want to think, well, what if I always took the derivative of an equation with respect to time? Well, that's kind of wonky because you're thinking, whoa, how the heck do I even do that? Because time's not even in this equation. Well, if I was taking it with respect to time, okay, I'm going to have to take derivative with respect to time, okay? And when I do this, okay, think implicit differentiation. Don't think anything else. It's all implicit differentiation, lots of notation, okay? So if I took, what would the derivative of a with respect to t be? Well, it would be dA dt equals, well, 2 pi r squared. Well, that's going to be, and I'm taking that with respect to t, well, that's going to be 2 pi, drop my power 1, and then I'm taking the derivative of r, so I have times a dr dt, okay? And what I end up having right here, okay, this right there, that is a related rates equation. It's relating the change in area with respect to the change in radius, okay? And if I really think about it, this equation relates the rate of change of area of a circle to the rate of change of its radius as the circle grows or shrinks at an instantaneous moment, okay? And like I said, it gets a little weird here because we're actually taking the derivative up here. Well, we're actually taking the derivative of an equation with respect to a variable that's not even there. You mean we can do that? Heck yeah, we can. We can do whatever we want, almost, in calculus here now. Okay, so let's kind of sit here. Let's come back. Let's start with a very basic example, okay? And think about doing this when you were a kid. You drop a stone into the water, and the radius of the ring is growing at a rate of 2 inches per second. And what they want us to know is how fast is the area? How fast is the area increasing when the radius is 3 inches? Well, how do I differentiate, no pun intended, how do I separate what we just did before with related rates? How do I change this? Well, the previous lesson, using differentials back there, we were looking for a specific quantity, right? We were estimating a particular quantity. And now here this problem is asking us something completely different. It's saying how fast. Well, how fast? That means at what rate is the area increasing? So I'm actually looking for a rate here, and there's buzzwords in there. If you're asked how fast makes you think related rates. We're going to relate the rate of the area to the rate of the changing radius. As a circle grows, the radius grows and the area grows, right? And this is one thing we need to keep going. Now, as we're cruising along here, use variables that make sense, because we're going to have to pick out given information and what they want us to know, okay? So what do we know? We drop a stone into the water, and the radius of the ring is growing. The radius is growing at a rate of 2 inches per second. Inches per second. Hey, that's a derivative, right? That really is kind of telling me the change in radius with respect to time equals 2 inches per second. My radius is growing at 2 inches per second, okay? What they want us to know is how fast is the area? What's the rate of the area? Well, that's kind of saying find dA dt when my radius is 3 inches, okay? Well, if I think about these back here when I'm writing these, okay, maybe I'm looking, in this case, maybe I'm looking for the change in area. Well, I have to know how my radius is changing, and I would also have to know my radius. So if I know 2 of these 3 variables, I can definitely solve for the third, right? But before I get there, well, if I'm looking for, this is what I need to find area, and given the radius, well, I need an equation that is going to relate the area in the radius of a ring or a circle. Well, that's not too bad. That is saying area equals pi r squared. That's a nice little equation that relates area with radius. Well, if I'm looking for how fast, if I'm looking for a rate, I'm looking for the change in area with respect to time, I'm going to differentiate with respect to time. When we see how fast and we're looking for a rate, that's a related rate, you will always differentiate a related rate problem with respect to time. And what this is going to give me, this is going to give me dA dt equals 2 pi r times dr dt. And if I need to know what dA dt is, the instantaneous moment when the radius is 3, and I know the radius changes at 2 inches per second, well, this is kind of cool. And it's really cool because everybody forgets to put their units on there. So let's look at this one. dA dt is going to equal 2 pi times, my radius is 3 inches, times dr is going to be 2 inches per second. And if I multiply all this stuff across, what do I get? Well, 2 times 3 is 6 times 2. That's going to give me 12 pi. And watch out, check out my units. Inches squared per second. That's what dA dt is. So at the instantaneous moment in time when the radius is 3 inches, my area is increasing at 12 pi inches squared per second, right there at that moment in time, okay? And what can we do here? Well, what happens if the radius is 6 inches? Well, no big deal. It really is not a big deal because I've already related my area and my R. So all I really have to do is come back here and plug and chug again. So this is really going to equal 2 times pi times 6 inches times dr dt. Well, that was what? 2 inches per second. Well, that's 2 times 6 times 2. That's going to hop me up to 24 pi inches squared per second. That's what dA dt is going to equal here. Okay? Units have to be on your answer. Okay? Only time units are not acceptable to be on the answer is if the original problem did not have units on it. Well, this one's a little bit different. How fast is the circumference changing when r is 8? Well, okay, so I know r is 8, and I still know it's the same problem. I still know dr dt was 2 inches per second. Well, now I need to be able to relate with an equation circumference with radius. Well, pretty sure you know circumference equals 2 pi r. I could also say circumference equals pi times diameter, but they gave me the rate of change of radius, so that's why I don't want that. But I could double the radius, and I could say the diameter would be going 2, right? Well, how fast? Find the rate. It says find dc dt when I know that information. So I write an equation to relate it. And if I'm looking for how fast, that's time, right? How fast is it growing? I differentiate with respect to time, and I get dc dt equals, well, 2 pi r. Well, that's going to be 2 pi r, drop to power 1, I get a 0, but I still have a dr dt. And how fast is the circumference changing? So dc dt would be what? 2 pi times 2 inches per second. And so my circumference, or dc dt, is going to equal 4 pi inches per second. And that should really kind of make sense because circumference is measured in a linear measure, not a squared measure, and your units will always make sense. If you put your units and multiply them through the problem, they will work themselves out in the end. You do not have to do that, but a lot of times it helps a lot, okay? So I'm only going to do one more example here, and we're going to be doing related rates today, tomorrow, and Wednesday. And we're going to do more and more and more, and we're going to work with related rates. We're going to think of circles and spheres and cones and cylinders and right triangles and squares and cubes and you name it. All different kinds of figures that can be changing. And what we're looking here is we're looking at the volume of a spherical balloon is inflating. This is important. It's inflating. That means it's growing at a rate of 800 pi inches cubed per minute. We'll look at my units. That would mean volume. So my change in volume with respect to time equals 800 pi inches cubed per minute. Okay? And they want to know how fast. How fast? That's a rate. This sounds like a related rate problem. How fast is the radius increasing at the instant r is 10? So find dr dt. How fast is the radius? Find dr dt when radius is exactly at 10 inches. Okay? Well, before I said this inflating is important because if they said I was deflating, my dv dt would have to be negative because it was getting smaller. So bigger, smaller, okay, your derivatives are going to carry signs with them as well, okay? Just like this previous one back here. The radius grew, I don't know why I just erased that, but the radius grew at a rate, that's why this rate is positive. If my circle were shrinking, it would be negative 2 inches per second, all right? So now I need to get here, volume of the sphere. Well, the good thing about related rates is they're always going to give you the formulas. You mean I don't have to know the volume of a sphere is 4/3 pi r cubed? That's exactly what I'm saying. The volume of a sphere is 4/3 pi r cubed. And if I need to find the rate, if I'm finding trying to find dr dt, given dv dt, how the heck do I even get a dv dt or a dr dt in there? Well, what I do is I come back and I differentiate with respect to time, okay? And that's how I introduce my dv dt's and all that good stuff in there. So I find out dv dt equals, this is a really cool thing here. When I take the derivative of volume of a sphere, 4/3 times 3 gives me 4 pi r squared when I drop it 1. Okay, that's the equation of the surface area of a sphere. But I took the derivative of r times dr dt, and there's my related rates equation. Okay, this is relating the change in volume with the change in the radius at any particular radius I want. In this case, the radius I want is 10. So I'm going to say, hey, ooh, a little bit different. We're solving for dr now. Well, dv dt, well, that's 800 pi equals, what do I have? I have 4 pi 10 squared times dr dt. Well, this is really 400 pi, isn't it? So if I divide off my 400 pi, I can see my pi's cancel, and I can see, oh. So dr dt is going to equal 2. Well, 2 what? Well, I don't know. What do you think? Radius. Should the radius be measured in inches cubed, inches squared, or an inch? Well, the cool thing is, this is what I think is kind of cool though. If I put my inches cubed and I also put on here, come on here now, if I put my inches in here, okay, so I'm going to have 10 inches, but then I square it. This is going to be in inches squared, so inches squared are going to divide out inches per second, right? And that's kind of cool, right? That is really pretty neat because this is inches cubed per second. I forgot to put my per second up there, okay? And we can keep hammering away with these. And how fast is the surface area increasing at this instant? What instant? What instant are we talking about? Well, we're talking about the instant when r equals 10 inches, right? At the instant when r equals 10 inches, and what do I know? Well, surface area. Well, you can call it surface area equals 4 pi r squared. Differentials typically have 2 letters, so you might want to make a kind of a fancy little s. Equals 4 pi r squared. Really doesn't matter. And this is what they want. How fast is surface area increasing? So they're saying find d fancy s dt when r is 10 inches. And what else do they want? Do we need anything else? I don't know. I don't know if we do or not. Do we need to know dr dt? What are we doing here? Well, let's check things out here. What are we going to do? Well, if I took the derivative of this with respect to time, I get d fancy s dt equals 8 pi r dr dt. Well, the only way to find the change in surface area, that gives me 8 pi. My radius, yep, it's 10 inches. Well, what the heck is dr dt at this exact moment in time? Whoa, check it out. Isn't that what we just created in the previous problem? Well, dr dt is 2 inches per second. So I'm going to grab that guy in here. I'm going to say 2 inches per second. And what does that give me? My surface area with respect to time is going to be, what does that get? Well, that's 2 times 10 is 20 times 8 would be 160 pi. But what are my units? Inches over 1, that's going to be inches squared per second at that moment in time when the radius is 10. If the radius is 12, my surface area is growing faster at that moment in time. Okay, it's going to change. So we're going to call her quits there for today. I'm just doing those 2 problems. If you want to go work and try to fumble through some of the homework for 4-6, you're welcome to. Tomorrow I'm going to do a few more examples, and I'm going to clean it up with a little bit of work time for the in-person people on Wednesday so they can ask some questions on it. But you can hold off until tomorrow if you wish. Before you start any homework, it might help kind of culminate things a little bit better if you hold off until tomorrow. But until tomorrow, have a good rest of your day. Bye-bye.